Alrighty, folks. Today we are going to begin our discussion of chemical bonding by talking about valence electrons. So let's get started. Our learning target for today is I know why atoms make chemical bonds. All right, I want you to go ahead and set up your notes today. Our topic is valence electrons, and the essential question is, why do atoms make chemical bonds? So go ahead and pause this video, set up your notes, and then press play when you're ready to go. All right, before we get into our content here, let's really quickly review the idea of negative numbers and how they work with addition and subtraction. So if I have 0 and I add -1 to it, I'm going to get -1. If I have 0 and I subtract -1 from it, I'm going to get +1. Okay? And so the reason that we're talking about this is because when we talk about valence electrons, we are talking about adding and removing or subtracting electrons. And each electron has a negative charge associated with it. So if we're adding an electron, we are adding a negative number to the charge of our atom. If we remove a negative number, we are removing a negative charge from our atom. So if you were to add two electrons, that would be similar to 0 plus -1 plus -1, and that would result in a charge of -2 because you added two negative numbers. You added two electrons, and therefore you get -2. If you were to take away three electrons, that would be similar to saying 0 minus -3. So you do 0 minus -3, you have an overall +3 or +3 charge. So however you think about it, whether you want to think about each electron individually or you want to think about the electrons as a whole, that's fine. But just remember, when we add a negative number, your result is a negative number. When we subtract a negative number, your result is a positive number. All right, so we have already introduced the idea of Lewis dot diagrams, but they're going to be very, very important as we start talking about bonding. So if you will open up your packet, you will find a Lewis dot diagram periodic table. And this is something that we have already done, and you're just going to really quickly do it again. And what I want you to do is I want you to pause this video. And what I want you to do when you pause is I want you to go ahead and fill out the Lewis dot diagrams for each of the first 20 elements. Remember, each group has the same number of valence electrons, so each vertical column. So go ahead and pause the video and fill out this periodic table. All right, so what you should have here is that each element in the first column has one dot next to it, or one valence electron. Second, two. Third, three. Fourth, four. Fifth, five. Sixth, six. Seventh, seven. And then in this eighth column, neon and argon have 8 dots around it. Helium has 2 dots. And that is because in the eighth column, we have full outer shells of electrons. The first energy level, the maximum number of electrons you can fit in that shell is 2. So helium has a full outer shell. It's just that its full shell is 2, whereas neon and argon's full shell is 8, but they have the similar properties. So we've got those completed. And then another thing you can write down is you see this for the valence electron, or for the first column where they all have one valence electron, that column is labeled A1. You can label this column, the second one where they have two, A2, where they have three, A3, A4, A5, A6, A7, and then A8. And that A tells the number after the A is going to tell you how many valence electrons you have. So we've got our Lewis dot diagrams. Now, if we look at our noble gases, we can see that our noble gases have full valence shells. Okay, helium has 2, and that's a full shell for helium. Neon has 8, that's a full shell for neon, and argon has 8, that's a full shell for argon. So when we think about atoms, they are at their most energetically stable when they have a full shell of valence electrons. And so all of these other elements, they want to be like noble gases. And so what that means is they are going to try to have their electrons look like the nearest noble gas. And they're going to do whatever they need to in order to get to the closest noble gas. So for fluorine, for example, the nearest noble gas is neon. So fluorine wants to look like neon. It has 7 valence electrons, neon has 8. And so fluorine's going to do whatever it can in order to get 8 valence electrons like neon. You have then something like lithium here. And lithium has 1 valence electron. Well, it can either try to look like neon or it can try to look like helium. Well, helium's a lot closer, so it's going to try to look like helium, and the way that it does that is by losing a single valence electron, and then it's going to have an outer shell that resembles that of helium because the next shell down from the valence shell is already full. So you can either try to look like you're trying to look like the closest noble gas, whether that is by adding electrons or by removing electrons. So ultimately, what this comes down to is what we call the octet rule. Atoms want to have 8 valence electrons, okay? Just like a noble gas. Uh, in reality, the octet rule should be atoms want to have a full outer shell, but for the most part, that means 8 valence electrons. If you're trying to look like helium, you'll have 2, but in general, our rule is 8. So this is going to be basically atoms want to look like or to have electron configurations similar to that of noble gases. So in order to get that, they have to transfer electrons. Those electrons, to look like a noble gas, have to come from somewhere else. And so they can either give away an electron or multiple electrons, or take an electron or multiple electrons. And so they are going to take the path of least resistance. So look here, right here at this animation. You can see that sodium has 1 valence electron and fluorine has 7. Well, sodium wants a full outer shell and fluorine wants a full outer shell. The easiest thing for both is for sodium to give up its 1 electron, so then its inner shell, which is already full, becomes its outer shell, and so it now has an electron configuration with a full outer shell. And fluorine gains an electron, so its outer shell becomes an octet, and so it is also satisfied and has an outer shell of 8 that resembles a noble gas. Both of them now have electron configurations that resemble helium. So what we can see here is for both of these, by sodium giving up an electron and by fluorine gaining an electron, they achieve the octet rule. What question does the previous slides answer? All right, so what we have here is we have a simulation where we can build an atom. So let's just go ahead and start off by building something like lithium. So I go ahead and I put in 3 protons, and then I'll just put in, we're not going to worry about neutrons right now, but what I want you to do is click on net charge. And what we're going to do is we're going to add electrons to lithium. Now lithium has 3 protons, so we are going to add 3 electrons. And what you'll see right now is that on the net charge, you have 3 positive charges from the protons and you have 3 negative charges from the electrons. Okay? And so the result is a net neutral charge, a 0 charge. Okay? And when an atom just exists on its own, it's just going to have that net neutral charge. However, when lithium is trying to look like the nearest noble gas, it's going to try to look like helium. And helium only has 2 electrons. So lithium is going to get rid of this electron in its outer shell, and it's going to be left with 2 electrons, okay? And still it has 3 protons. So when you look at the net charge now, we now have 1 more proton than we have electrons, and therefore we have a net charge of +1. And so this results in a charged atom or an ion. So let's really quickly go ahead and build another atom. Let's bump up to oxygen. So we're going to need 8 in here. All right. And then we need 8 valence electrons, or we need 8 total electrons, and 6 of those will be valence. Okay. All right. So for oxygen, when we have our neutral oxygen, you can see we have 8 protons, we have 8 electrons. Now, oxygen wants to look like the nearest noble gas. And for oxygen, that's going to be neon. So we are going to go ahead and we are going to add 2 electrons because even though helium is there, it would take 6 electrons to look like helium, whereas it only takes 2 to look like neon. So we want to take the path of least resistance. So if we add 2, we can see oxygen now looks like neon. It has that electron configuration of neon, but it now has 2 more electrons than it does protons. And so we went from a neutral atom and we added 2 electrons, 0 plus -2, and we have an overall charge of -2. So this is the idea of how an ion is formed. So an ion is a charged atom. And what that means is that electrons have either been gained or lost. And we were just in that previous simulation, we were just adding and taking away electrons willy-nilly. But in reality, those electrons are coming from other elements. And so once again, we're looking at this animation between sodium and fluorine, and you can see sodium loses its electron and fluorine gains that electron. And that's where those electrons move to and from. And so remember, these electrons in ions are going to match the nearest noble gas, so we are able to figure out how many electrons each atom gains or loses, and therefore what the charge on that atom would be. What question does the previous slides answer? All right, so on your handout, I want you to flip back to it. You will see below where we have the Lewis periodic table, we have a section for you to write the cations and anions for groups A1 through A3 and A5 through A7. Don't worry about A4 right now. But what we're going to look at is we're going to figure out, okay, when these atoms form ions, when they take on the electron configuration of the nearest noble gas, what charge do they take on? And because all of these atoms have, or in these columns have the same valence electrons, we should see a pattern emerge. So all right, let's go ahead now and go and build some atoms. We're actually going to start with lithium because hydrogen's a little weird. But go ahead and build lithium. So lithium has 1, 2, 3 protons. And make sure you open up the net charge. And we're going to add 1, 2, 3 electrons. And that brings us to the neutral version of lithium. So what we're going to do is we're going to make lithium look like the nearest noble gas. Well, you have 2 choices. You have neon or you have helium. Remember, this right-hand column is going to be the noble gases. So lithium is closest to helium. So we're going to go ahead and make lithium look like helium. That means it's going to have 2 electrons. So we take away 1 electron. And the result is that lithium forms a +1 ion. So what you would do is on your the ions section of your handout next to lithium, you would write +1. Now let's go ahead and make beryllium. Okay, beryllium has 4 protons and it has 4 electrons, and you can see that's neutral. What is the nearest noble gas to beryllium? Well, helium or neon. Helium is closer, so we need to make beryllium have 2 electrons. So we take away 1, 2 electrons. And now we see that beryllium has a +2 charge when it forms an ion. So you're going to continue to do this for each of the elements listed. You can only use this simulation to kind of figure out this first row here. But what I hope you see is that a pattern emerges as you do this. So go ahead and use this simulation to fill out that first row. Don't worry about hydrogen. And then see if you can figure out the next row on your own. Alrighty, so what we're looking at here is that lithium, sodium, and potassium all have all make charges of +1 ions. Beryllium, magnesium, and calcium all make +2 charges when it comes to ions. Boron and aluminum make +3 ions. Nitrogen and phosphorus, because they are now closer to the noble gas that is higher in atomic number, they're going to start gaining electrons. And so nitrogen and phosphorus both make -3 ions. Oxygen and sulfur make -2, and fluorine and chlorine make -1. For the sake of this class, we're going to just go ahead and say that hydrogen makes a +1 ion. Um, it gets a little complex with hydrogen. Hydrogen is just weird, but just for the sake of argument, we're going to say that hydrogen makes a +1. So go ahead and make sure you fill this out. For this worksheet, you can check the key after you're done with this lecture to make sure that you filled it out correctly. If you have any questions, please reach out to your teacher. All right, so what you should notice now is that all of the ions on the left-hand side of your periodic table make positive ions. And these positive ions have a name. They are called cations. A cation is a positively charged atom due to loss of electrons. All of those elements, those atoms on the left-hand side of your periodic table that we did, they lost electrons. And so they became positively charged. And just in general, metals become cations. Okay? So we'll get more into what that means later. But to kind of help you remember that a cation is a positive ion, we're going to remember that a cation, a cat, you see that cat there, is an ion with a positive charge. You see pause like cat? I know, awesome. It's also the cutest ion ever. Look how cute that ion is. Obviously, ions aren't actually cats, but hey, good way to remember. Also, the way I learned it is that the T in the middle of cation, that T kind of looks like a plus sign, so that kind of helps you remember. Next, on the right-hand side, you'll notice that all of the elements on the right-hand side became negatively charged because they gained electrons, and those are called anions. So an anion is a negatively charged atom due to gaining an electron or more. Non-metals become anions, and once again, we'll talk more about what that means in the future, but that right-hand section of the periodic table, you remember, is going to be your anions, and that left-hand section of the periodic table, your metals, is going to be cations. So cats are good, positive. Onions are bad, negative. I personally like onions, but if you've ever tried to eat an onion raw, you probably had a bad time with it. So we're just going to remember that onions are negative. Okay? So cations are positive, anions, onions are negative. What question does the previous slides answer? Alrighty, folks, so that's it for valence electrons today. I want you to go ahead and take this ungraded quiz and pause the video to take the quiz and then come on back and we'll talk about what the correct answers are. All right, how many electrons does an atom want in its valence shell? It's going to want 8 because that is what noble gases have. How many valence electrons does magnesium have in its valence shell? So if you look at your periodic table, you'll see that magnesium is in that second column and therefore has 2 valence electrons. Would magnesium gain or lose electrons to make an octet? Well, magnesium, because it's on that left-hand side, it becomes a cation, and it's easier for it to lose 2 electrons than gain 6, and so it would lose electrons. And finally, what would the charge of a magnesium ion be? Because magnesium loses 2 electrons, that means you do 0 minus -2, and you get +2. So if you answered those questions like that, you should have gotten a perfect score. Alrighty, folks, I want you to go ahead and self-assess. How well do you understand valence electrons on a scale of 1 to 5? 1 is I'm super lost. 5 is I'm ready to teach this, or you could teach this to someone else. This is just an opportunity for you to kind of see where you're at and what you need. Alrighty, folks, so that's it for valence electrons. Make sure that you check your handout against the key that's posted in Schoology. And if you have any questions, please reach out to your teacher. Have a great day.